Hey everyone, and welcome. When you first look at the Ishikagu syllabus, it can feel, well, a little intense, right? It's packed with information, but don't worry, that's what we're here for. Today, we're going to break it all down and turn that dense document into a super clear roadmap for your journey into AI. So let's jump right in. Okay, so the first and most important thing to get about the 2024 syllabus is its core philosophy. It's right here in this quote from the official guide. The focus has gotten really, really sharp. It's all about building a rock-solid foundation in the fundamental algorithms. This isn't about chasing the latest shiny object. It's about deeply understanding how this stuff actually works, right from the ground up. And hey, if you're just hearing about this for the first time, the Ishikaku is basically Japan's top-tier certification for deep learning engineers. It's a real benchmark of expertise. So think of what we're doing here as your guided tour. We're not going to get you lost in the weeds of every single formula, but we are going to map out the entire landscape so you can see how it all fits together and navigate it with confidence. So here's our game plan. This is the path we're going to take together. We'll start with the syllabus itself, and then we're going to build from the ground up. We'll dive into the math that makes AI possible, then move to the basics of machine learning, and then into the powerhouse that is deep learning. After that, we'll get to the fun stuff, seeing real-world applications, before we finish up with how you actually get these models out into the world. It's the whole journey, from theory to reality. First up, math. Now, I know, for some of you that might sound a little scary, but hang with me here. Don't think of this as a hurdle. It's the language of AI. It's the set of rules we absolutely need to know to build and understand these intelligent systems. Everything else we talk about today is built right on top of this. So, the first part of that language is linear algebra. And what's it all about? Well, it gives our data shape. See, to an AI, a picture of a cat isn't a cat. It's just a giant grid of pixel values, a matrix. A sentence isn't just words, it's a sequence of numbers called vectors. Linear algebra is the grammar that lets us work with these shapes and manipulate all that data efficiently. Right, but the real world isn't neat and tidy. It's messy, it's uncertain, and our AI needs a way to handle that. That's exactly where probability and statistics come in. This is the part of the language that deals with uncertainty. It allows our models to make educated guesses and, crucially, to tell us how confident they are in those guesses. It's all about handling the maybes of the world. And finally, our model is learning, but is it actually getting any better? How do we even tell? That's the question that information theory answers. It gives us the tools to measure information, and more importantly, to measure error. It's like a report card for our AI, using concepts like KL divergence to tell us exactly how far off our model's predictions are from the truth. All right, so we've got our language, our math, all sorted. Now we can actually start building. We're moving up to the next layer, the core ideas behind machine learning. This is where we put that math to work and actually teach computers to find patterns in data all by themselves. Now, this is a super important distinction, so let's clear it up right now. You'll hear machine learning and deep learning a lot. Machine learning is the big, broad field of algorithms that learn from data. Deep learning, which we'll get to in a sec, is a very powerful subset of that. Think of it this way. Machine learning is the entire category of cars, while deep learning is the super high-performance Formula One engine that's been breaking all the records lately. So how does this learning thing actually happen? Well, for supervised learning, it's a lot like studying with flashcards. It's this beautiful, simple loop. You show the model some data that's already labeled, like a picture of a dog with the label dog. The model makes a guess. You calculate how wrong that guess was. Then you adjust the model's internal wiring just a tiny bit to make it better next time. You do that millions of times, and pretty soon it gets really good at recognizing dogs. And of course, there's a whole world inside ML that the syllabus covers. You've got the different styles of learning, not just with labeled data, but with unlabeled data too. You'll learn the classic workhorse models like linear regression, and you'll dive into the big challenges, the things that keep engineers up at night, like overfitting. That's when a model just memorizes the answers instead of actually learning. And you'll learn the essential tricks, like regularization, to stop that from happening. Okay, buckle up. We've got the engine. We understand the basics of how it works. Now it's time to add the supercharger. We're stepping into the world of deep learning. This is what's behind almost all of the incredible AI breakthroughs you read about in the news. So what's the magic that makes these massive networks learn? Well, it's a really clever algorithm called backpropagation. Basically, data flows forward through the network and it makes a prediction. We see how wrong it is. Then the magic happens. the error signal flows backward through the network. It's like a really efficient blame game where every connection figures out how much it contributed to the mistake and adjusts itself to do better next time.
Now, you can't just build these giant networks and hope for the best. You need a specialized toolkit to tune them up and get them to learn properly. This includes powerful optimizers like Atom. Think of it as a super smart GPS for your model, always finding the fastest route to a better answer. It also includes clever tricks like dropout to prevent that pesky overfitting, and smart ways to set up the network at the very beginning so it has a good head start.
And what's so cool is you can actually see the history of modern AI just by looking at the evolution of these architectures. First, CNNs came along and just completely cracked the code for understanding images. Then, RNNs arrived, which were specifically designed to handle sequences, like words in a sentence. And then, bam, 2017. The transformer architecture hits the scene with this thing called self-attention, and it changes absolutely everything, especially for language. All right, we've done the hard work. We have the theory, the math, the models. Now for the really fun part. Let's see what we can actually build with all this. This is where all that theory hits the real world. One of the biggest and most visual areas is, of course, computer vision. And we're talking about going way beyond just saying, that's a cat in a picture. We're talking about being able to draw a perfect box around the cat, or even color in every single pixel that belongs to the cat. It's about a deep, granular understanding of images. And the syllabus makes sure you know the heavy hitters in this space. You've got ResNet, which famously allowed us to train networks that were hundreds of layers deep. You've got the Vision Transformer, or VIT, which proved that the transformer architecture was amazing for more than just text. And then you have models like YOLO, which are just insane for doing real-time object detection in videos. Okay, moving from sight to language, now we're talking about natural language processing. This is all about teaching computers to understand, process, and even generate human language. This is the tech behind the scenes of your smart assistants, translation apps, and yeah, all of those massive language models that are everywhere right now.
And here, you're going to meet the absolute rock stars of modern NLP. BERT was a total game changer because it learned to understand context by looking at a whole sentence at once. The GPT family, of course, wrote the playbook for the huge models we see today. The syllabus also gets into the purely creative side of AI, with models like GANs that can generate brand new, stunningly realistic images from scratch. But here's the thing. Building a cool, powerful model on your laptop is one thing. Getting it to actually work out there in the real world reliably for millions of people, that's the final and maybe the toughest part of the whole race. Think about it. These models can be absolutely gigantic. You can't just cram a 100-gigabyte model onto someone's smartphone. So, the syllabus covers these super important tricks for making models smaller, faster, and more efficient without losing performance. And, of course, it covers how to use the right kind of specialized hardware, like GPUs, to give them the horsepower they need to run fast. And where does this AI code actually live? Well, the syllabus covers all the modern approaches. Sometimes it runs right on your phone or your smart speaker. That's edge computing. You'll also learn about essential tools like Docker to package everything up so it runs the same way everywhere. And then there's this really cool idea called federated learning, where a model can learn from everyone's data without ever seeing anyone's private information. Super clever stuff. So there you have it. That's the whole journey. We went from the elegance of linear algebra all the way through machine learning and deep learning to the exciting applications and finally to the nitty-gritty of putting a model into production. You've seen the full picture. The eShikaku syllabus is the map to this entire incredible world. So the only question left is, where are you going to explore first?